Imagine a black hole so massive that it weighs as much as 66 billion suns. A cosmic monster so enormous that its event horizon is 40 times larger than our entire solar system. A gravitational beast so powerful that it would take light an entire week to cross from one side to the other. This isn't science fiction. This isn't an exaggeration. This is TON 618, and it's the most massive black hole we've ever discovered. Today, we're going to explore this cosmic leviathan in complete detail. We'll understand what makes it so incredibly massive, how it grew to such unfathomable size, and what it tells us about the violent, extreme universe we live in. By the end of this video, you'll understand why TON 618 represents one of the greatest mysteries in modern astrophysics. But before we dive into the heart of this cosmic monster, I need 3 things from you. First, hit that subscribe button right now. We're exploring the most extreme phenomena in the universe, and you don't want to miss a single video. Second, smash that like button. It helps this video reach more people who are fascinated by the universe's most extreme objects. And third, drop a comment below telling me what you think would happen if TON 618 suddenly appeared in our galaxy. I'll be reading and responding to your comments. Now, let's journey 10.4 billion light-years into the cosmos to meet the biggest black hole ever found. TON 618 was first catalogued in 1957 by astronomers using the Tonantzintla Observatory in Mexico. The TON stands for Tonantzintla, and 618 is simply its catalog number. But at the time of its discovery, nobody realized they were looking at one of the most extreme objects in the entire universe. For decades, TON 618 was simply classified as a faint blue star. It wasn't until the 1970 seconds and 1980 seconds, when astronomers developed better spectroscopic techniques, that they realized this wasn't a star at all. It was something far more exotic. A quasar. Quasars are among the most luminous and energetic objects in the universe. They're powered by supermassive black holes at the centers of distant galaxies, actively feeding on enormous amounts of matter. As this matter spirals into the black hole, it forms an accretion disk that heats up to millions of degrees, emitting tremendous amounts of radiation across the entire electromagnetic spectrum. TON 618 is one of the brightest quasars ever discovered. It shines with the luminosity of 140 trillion suns. Let that number sink in for a moment. This single object outshines our entire galaxy by a factor of thousands. If TON 618 were placed at the distance of Sirius, the brightest star in our night sky at just 8.6 light-years away, it would shine as bright as the sun in our sky, despite being a point source. But the true nature of TON 618's extreme size wasn't understood until more recent measurements in the 21st century. Using advanced techniques to measure the black hole's mass, astronomers discovered that TON 618 contains approximately 66 billion solar masses. Some estimates range from 40 to 66 billion solar masses, but even the lower estimate makes it one of the most massive black holes ever found. To put this in perspective, the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A*, has a mass of about 4 million solar masses. TON 618 is more than 16,000 times more massive. It's not just bigger, it's in a completely different category of cosmic monsters. Before we dive deeper into TON 618 specifically, we need to understand what black holes are and how they form. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside it. This boundary of no return is called the event horizon. Black holes come in different sizes. Stellar mass black holes form when massive stars collapse at the end of their lives. These typically range from about 5 to 100 solar masses. Then there are intermediate mass black holes, ranging from hundreds to thousands of solar masses, though these are rare and poorly understood. Finally, there are supermassive black holes, which lurk at the centers of most large galaxies. These range from millions to billions of solar masses. TON 618 falls into this category, but it's at the absolute extreme end of the scale. The size of a black hole is typically described by its Schwarzschild radius, which defines the event horizon. For a non-rotating black hole, this radius is directly proportional to its mass. The formula is elegant. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For TON 618, with its mass of 66 billion solar masses, this calculation gives us an event horizon with a radius of approximately 195 billion kilometers, or about 1,300 astronomical units. That means the diameter of the event horizon is about 390 billion kilometers, or 2,600 AU. To put this in perspective, Neptune, the outermost planet in our solar system, orbits at about 30 AU from the Sunday. The event horizon of TON 618 is nearly 87 times larger than Neptune's orbit. If you place TON 618 at the center of our solar system, its event horizon would extend far beyond the orbit of Pluto, beyond the Kuiper belt, reaching about 40 times the size of our entire solar system. The Voyager 1 spacecraft, which has been traveling for over 45 years and is the most distant human-made object, is currently about 160 AU from the Sun. Even at that incredible distance, it would still be well within the event horizon of TON 618. TON 618 isn't just a black hole sitting quietly in space. It's an active quasar, which means it's actively feeding on enormous amounts of matter. Understanding this process is key to understanding why TON 618 is so luminous and how we detected it from 10.4 billion light-years away. When matter falls toward a black hole, it doesn't fall straight in. Due to conservation of angular momentum, the matter forms a rotating disk called an accretion disk. As particles in this disk spiral inward, they collide with each other, generating tremendous friction. This friction heats the disk to millions of degrees Celsius. At these temperatures, the accretion disk emits radiation across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The region near a supermassive black hole becomes one of the most energetic environments in the universe. For TON 618, the accretion disk is feeding the black hole at an incredible rate. Estimates suggest it's consuming matter equivalent to thousands of Earth masses every single day. This voracious appetite is what makes it shine with the luminosity of 140 trillion suns. The quasar also produces powerful jets of particles and radiation that shoot out from the poles of the black hole at nearly the speed of light. These jets can extend for hundreds of thousands of light-years into space, far beyond the host galaxy itself. The energy output from TON 618 is almost incomprehensible. Every second, it radiates more energy than our sun will produce in its entire 10 billion-year lifetime. This energy is so intense that if Earth were somehow transported to within a few light-years of TON 618, the radiation would instantly vaporize our planet and everyone on it. Quasars were much more common in the early universe. TON 618 existed when the universe was only about 3 billion years old, less than a quarter of its current age. This was an epoch when galaxies were forming rapidly, merging frequently, and supermassive black holes were growing quickly by consuming vast amounts of gas and stars. Today, most supermassive black holes are relatively quiet, including the one in our own galaxy. They've consumed most of the available matter in their vicinity, and now sit dormant, occasionally snacking on a wayward star or gas cloud. TON 618 gives us a window into what these monsters were like in their prime, billions of years ago. Let's truly grasp the scale of TON 618 through comparisons. Numbers like 66 billion solar masses are so large they become abstract. We need concrete comparisons to understand what we're dealing with. First, let's compare TON 618 to Sagittarius A*, the supermassive black hole at the center of the Milky Way. Sagittarius A times has a mass of about 4 million solar masses. TON 618 is 16,500 times more massive. If Sagittarius A times were a marble, TON 618 would be a massive boulder over 2 meters in diameter. The event horizon of Sagittarius A times has a diameter of about 24 million kilometers, roughly 17 times the diameter of the Sunday. That sounds enormous, and it is. But TON 618's event horizon has a diameter of 390 billion kilometers. It's more than 16,000 times larger in diameter than Sagittarius A*'s event horizon. Let's think about this in terms of travel time. Light, the fastest thing in the universe, travels at 300,000 kilometers per second. It takes light about 8 minutes to travel from the Sun to Earth. It takes light about 5.5 hours to travel from the Sun to Pluto at its average distance. To cross the diameter of TON 618's event horizon, light would need to travel for about 15 days. That's right, even at the speed of light, it would take more than 2 weeks to go from one side of this black hole's event horizon to the other. If you could somehow build a highway around the event horizon of TON 618 and drive at 100 kilometers per hour without stopping, it would take you about 140,000 years to complete one lap. For comparison, modern humans have only existed for about 300,000 years. The mass comparison is equally mind-boggling. Our Sun has a mass of about 2 times 10 circumflex 30 kilograms. That's a 2 followed by 30 zeros. TON 618 has a mass of about 1.3 times 10 circumflex 41 kilograms. To visualize this, if every star in the Milky Way galaxy, roughly 200 to 400 billion stars, were like our Sun, and you combine them all together, you'd still need to add about 300 to 600 more Milky Way galaxies worth of stars to equal the mass of TON 618. The gravitational pull of TON 618 is equally extreme. If you were somehow able to orbit just outside the event horizon without falling in, you'd experience time dilation effects, where time would pass much more slowly for you than for someone far away from the black hole. 1 hour near the event horizon could equal years or even decades of time passing in the outside universe, depending on your exact distance. Here's where things get really interesting and mysterious. How did TON 618 grow to such an enormous size? This is one of the biggest unsolved puzzles in astrophysics. The universe is approximately 13.8 billion years old. TON 618 is located 10.4 billion light-years away, which means we're seeing it as it was 10.4 billion years ago when the universe was only about 3.4 billion years old. This means TON 618 had only 3.4 billion years to grow from whatever seed black hole started its formation to its current mass of 66 billion solar masses. This presents a serious problem. Black holes grow by consuming matter, but there's a limit to how fast they can grow called the Eddington limit. This limit exists because as a black hole accretes matter, the infalling material heats up and emits radiation. This radiation creates an outward pressure that pushes against the infalling matter. If the black hole tries to eat too quickly, the radiation pressure becomes so strong that it blows away the incoming matter, preventing further growth. The Eddington limit means that a black hole can roughly double its mass every 10 to 100 million years, assuming it's constantly feeding at the maximum rate. Starting from a stellar mass black hole of, say, 100 solar masses, and doubling every 10 million years for 3.4 billion years, you could reach a mass of about 10 circumflex, 51 solar masses, a number so large, it's meaningless. Clearly, black holes don't continuously feed at the Eddington limit. More realistic models suggest that supermassive black holes grow through a combination of steady accretion and occasional bursts of rapid growth, particularly during galaxy mergers. When two galaxies collide, their supermassive black holes eventually merge, instantly creating a more massive black hole. Additionally, the merger stirs up huge amounts of gas that can then be funneled toward the black hole, providing fuel for rapid growth. But even with these processes, growing to 66 billion solar masses in just 3.4 billion years is challenging. Some astronomers propose that TON 618 and other extremely massive early black holes might have formed from direct collapse black holes. Instead of forming from a single star, these black holes could have formed when huge clouds of primordial gas collapsed directly into black holes with masses of tens of thousands or even millions of solar masses right from the start. Starting with a much larger seed black hole would make it easier to reach 66 billion solar masses in the available time. Another possibility is that the early universe had physical conditions that allowed black holes to exceed the Eddington limit temporarily, growing faster than we think possible. There's also the possibility that our understanding of the early universe is incomplete. Perhaps the conditions 10 to 12 billion years ago were so different from today that black hole growth proceeded through mechanisms we haven't fully considered. The growth of TON 618 remains an active area of research. Understanding how such massive black holes formed so early in cosmic history is crucial for understanding galaxy evolution, the formation of structure in the universe, and the physics of extreme gravity. While TON 618 is often called the most massive black hole ever discovered, it's important to understand the context and the competition. The universe of supermassive black holes is constantly being updated as we make new discoveries and refine our measurements. Several other black holes compete for the title of most massive. Phoenix A, the central black hole of the Phoenix cluster, has an estimated mass of around 100 billion solar masses. Though this measurement has significant uncertainty, if confirmed, Phoenix A would be even more massive than TON 618. Holmberg 15 amperes. The central black hole in the galaxy Holm 15 amperes has been estimated to have a mass between 40 and 310 billion solar masses, though the large uncertainty range makes it difficult to say definitively. IC 1101, one of the largest galaxies known, likely harbors a black hole of 40 to 100 billion solar masses at its core. The challenge with measuring these extreme black holes is that they're so distant and so massive that our measurement techniques have large uncertainties. We typically measure black hole masses by observing the motion of stars or gas near the black hole and using orbital dynamics to infer the mass. But at distances of billions of light years, these measurements become increasingly difficult. For TON 618 specifically, the mass estimate of 66 billion solar masses comes from analyzing the quasar's spectrum and applying relationships between the black hole mass and the properties of the surrounding gas. This method has uncertainties, which is why some sources cite a range of 40 to 66 billion solar masses. Regardless of whether TON 618 is the absolute most massive, it's certainly among the top contenders and represents the extreme upper end of supermassive black hole masses. What makes TON 618 particularly notable is that it's one of the most well-studied ultramassive black holes due to its brightness as a quasar. It's also worth noting that TON 618 is not in our local universe. At 10.4 billion light-years away, we're seeing it as it existed in the early universe. The black holes competing for the most massive title are spread across different cosmic epochs. Some, like those in nearby galaxy clusters, are relatively close and represent black holes in the modern universe. Others, like TON 618, are ancient quasars, showing us what these monsters were like billions of years ago. This temporal distribution tells us something important. The most massive black holes formed early in cosmic history, during an era of rapid galaxy formation and mergers. Today's universe is more settled, and while supermassive black holes continue to grow, they do so much more slowly. Let's engage in a thought experiment. What would happen if TON 618 suddenly appeared in our cosmic neighborhood? This hypothetical scenario helps us understand just how extreme this object truly is. First, let's imagine TON 618 replaced Sagittarius A times at the center of our Milky Way galaxy. Remember, TON 618 is 16,500 times more massive than Sagittarius A*. This massive increase in the central black hole's mass would have dramatic effects on our galaxy. The increased gravitational pull would affect the orbits of stars near the galactic center. Many stars would be pulled into tighter, faster orbits, while others might be ejected from the galaxy entirely through gravitational slingshot effects. The overall structure of the galaxy would begin to change, though these changes would take millions of years to manifest across the galaxy's 100,000 light-year diameter. But the immediate challenge wouldn't be the gravity, it would be the radiation. If TON 618 were actively feeding as a quasar at the center of our galaxy, the radiation output would be extreme for life in the Milky Way. Remember, TON 618 shines with the luminosity of 140 trillion suns. Earth is located about 26,000 light-years from the galactic center. Even at this vast distance, the radiation from an active TON 618 would be intense. The X-rays and gamma rays alone would likely strip away Earth's ozone layer within years or decades, leaving our planet vulnerable to intense solar and cosmic radiation. Complex life would become impossible, and even microbial life would face extreme challenges. Any planets within a few thousand light-years of the galactic center would become completely uninhabitable. The radiation would be so intense that planetary atmospheres would be blown away, and surface temperatures would soar to thousands of degrees. Now let's imagine an even more extreme scenario: TON 618 appearing in our solar system, replacing the Sunday. This would have immediate and dramatic consequences. The event horizon alone, at 2,600 AU in diameter, would extend far beyond Pluto's orbit at 40 AU. Earth, at just 1 AU from the center, would be well within the event horizon. We wouldn't even have time to realize what happened. Earth would be inside the black hole instantly, pulled apart by extreme tidal forces as it fell toward the singularity. Even if we placed TON 618 farther away, say at the distance of the nearest star system, Alpha Centauri at 4.3 light-years, the effects would still be severe. If it were active as a quasar, the radiation would be comparable to having multiple suns in our sky, potentially making Earth uninhabitable. The gravitational influence would begin to perturb the orbits of objects in the outer solar system, though this would take thousands of years to significantly affect the inner planets. These thought experiments highlight just how extreme TON 618 is. It's an object that exists on a scale that makes even our solar system seem tiny by comparison. It's a reminder that the universe contains phenomena far beyond our everyday experience, operating on scales of power and size that challenge our imagination. What will happen to TON 618 inches the future? Like all black holes, its ultimate fate is determined by the laws of physics and the evolution of the universe. Currently, as we see it 10.4 billion years ago, TON 618 is an active quasar, feeding voraciously on surrounding matter. But quasars don't stay active forever. Eventually, a quasar consumes or blows away the available gas and dust in its vicinity. Without fuel, the accretion disk fades, the brilliant radiation diminishes, and the quasar becomes dormant. In the present day, meaning 10.4 billion years after the light we see left, TON 618, the black hole has likely long since become quiescent. It probably sits quietly at the center of a massive elliptical galaxy, only occasionally flaring up when an unfortunate star wanders too close, or when the host galaxy experiences a minor merger that brings in fresh gas. Over truly cosmic timescales, trillions upon trillions of years, even black holes are not eternal. Stephen Hawking discovered that black holes emit a form of radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation causes black holes to very slowly lose mass. For a black hole the size of TON 618, the timescale for evaporation through Hawking radiation is almost incomprehensibly long. A rough calculation suggests it would take approximately 10 circumflex 100 years, that's 1, followed by 100 zeros, for TON 618 to completely evaporate. For comparison, the current age of the universe is only about 10 circumflex 10 years. The evaporation of TON 618 would take a Google 10 circumflex 100 years, a timescale so vast that it has no practical meaning in our universe. Long before TON 618 evaporates, the universe itself will have changed beyond recognition. Stars will have long since stopped forming as the universe runs out of hydrogen gas. Existing stars will have all died, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will have merged or drifted apart due to cosmic expansion. The universe will have entered what's called the black hole era, where black holes are the dominant remaining structures. Eventually, even these black holes will evaporate, leaving behind a universe of nothing but radiation cooling toward absolute zero. But that's so far in the future that it's almost meaningless to contemplate. For now, TON 618 exists as one of the universe's ultimate monuments to the power of gravity and the extreme conditions that can exist in our cosmos. TON 618 is more than just a black hole. It's a window into the extreme universe, a testament to the incredible forces and scales that exist in our cosmos. With a mass of 66 billion suns and an event horizon 40 times larger than our solar system, it represents one of the most extreme objects we've ever discovered. The existence of TON 618 raises profound questions. How did it grow so massive in such a relatively short time? What was the early universe like that it could produce such monsters? Are there even larger black holes waiting to be discovered? These questions drive ongoing research in astrophysics and cosmology. TON 618 also serves as a reminder of our place in the universe. We live on a small planet orbiting an average star in a typical spiral galaxy. Our supermassive black hole, Sagittarius A*, while massive by our standards, is dwarfed by TON 618. The universe operates on scales that humble our human perspective. Yet we should also feel a sense of wonder and pride. Despite our small size, we humans have discovered and measured objects like TON 618. We've peered 10.4 billion light-years into space and time. We've calculated the mass of an object we'll never visit, using nothing but light and mathematics. That's an incredible achievement of human curiosity and ingenuity. The study of ultramassive black holes like TON 618 continues. New telescopes and techniques are allowing us to discover more of these objects and measure their properties with greater precision. Each discovery adds to our understanding of how the universe formed and evolved, how galaxies grow, and how the extreme physics of gravity operates in nature's most powerful laboratories. So, that's TON 618. A black hole so massive it defies easy comprehension, a cosmic monster lurking in the distant universe, a challenge to our understanding of physics and cosmology. What do you think about TON 618? Does it terrify you, fascinate you, or both? What questions do you have about black holes in the extreme universe? Drop your thoughts in the comments below. I read every comment and love hearing your perspectives. If this video expanded your understanding of the universe and its most extreme phenomena, please hit that like button. It really helps the video reach more people who share our passion for cosmic exploration. And if you haven't already, subscribe and click the notification bell. We're exploring the universe's greatest mysteries, and you don't want to miss what's next. Share this video with anyone who loves space, anyone who's fascinated by black holes, anyone who wants to understand the extreme limits of nature. Let's spread the knowledge about these incredible cosmic phenomena. Thank you for joining me on this journey to the heart of one of the universe's greatest monsters. Until next time, keep looking up, keep asking questions, and keep exploring the cosmos. The universe is vast, strange, and full of wonders like TON 618, waiting to challenge and amaze us. Clear skies, everyone.